Right, we'll now show you circular convolution. Remember, our Hn is equals to 1, 2, and 3 from index 0, 1, 2, and nothing else outside. And in this example, when we perform a delay by one sample, we are getting 0, 1, 2, 3. And we are basically shifting these 3 samples right hand side, and zeros are being shifted in because the original sequence have zeros on the left. Now, what about circular convolution? In this particular case, we realize that if Hn is represented or periodic with 3 samples, then Hn is actually these 3 samples, and on the left hand side, they are not zeros, they are just the previous repeating 3 samples. So what happened when Hn minus 1? So it would not be the same as this result. Instead, this peak, this peak will be shifted into here, and Hn minus 1 is 3, 1, 2. And of course, this is going to cause a problem because it is not linear convolution anymore. It is circular convolution. But let us examine what happens when we perform circular convolution with n equals to 3. Well, we still have our input sequence x, which is 1, 1, and our h is 1, 2, 3. And now let's use n equals to 3. When we have n equals to 3, we are saying that this sequence will repeat every 3 samples. So these 3 samples, so it is actually 1, 1, 0, 1, 1, 0, 1, 1, 0, and so on for this sequence. And our friend here is 1, 2, 3, 1, 2, 3, and so on until infinity. Okay, so it will repeat both on the left hand side and the right hand side for n equals to 3. Right, so now we can draw Hn, and we can draw Hn minus 1 that is with period 3. So we realize that Hn minus 1 looks like this, and where does it occur? It occurs when we are using this equation for our circular convolution. So remember, the difference is only here. Let's expand this circular convolution equation. Again, we only have xk equals to 0 and k equals to 1. So we have x of 0 and x of 1. There's no change. And our h now, of course, we have to write it as with this n modulo at 3 index. H of n with modulo 3 minus 0. So this is actually exactly h of n. So nothing changed. This is exactly x of 0, h of n as in our previous case. This guy, x of 1 is still 1. There's no change here, but this has changed from, this is not the same as h of n minus 1 in our previous case. This is hn modulo 3, n minus 1 modulo 3, and this is being shifted in. So now we are going to sum. So it's 1 plus 3 is equals to 4 because they are aligned here. 2 plus 1 is equals to 3. 3 plus 2 equals to 5. So this is our output. And this, of course, is not the same as what we have predicted in the linear convolution case. In the linear convolution, y of n is equals to 1, 3, 5, 3. 0, 0, 0, and so on. So it got these 2 values right. The first value is wrong. Okay, how do I show you that this is also the result if I use the frequency domain DFT? So DFT, I will take the 3 samples and I will DFT it. In actual fact, we always use FFT because FFT is the fast version of DFT. That's all. And we'll also take 3 samples of the H, and so there is the big N part, right? We're taking 3 samples. So what we do is we first convert x to be xk. So this is getting xk, and this is getting hk, and we are then multiplying it term by term, and then we are inverse FFT it to get our output y. And this is 435, and 435 exactly agrees with this 435 here. So So we now know how to do it by circular convolution way. We know how to do it by the frequency representation way using FFT or DFT, using capital N equals to 3. So the result is wrong. What can we do? So let's try n equals to 4. And 0 padding is the answer. So when we go from n equals to 3 to n equals to 4, what are we saying? We are now saying that we are padding the extra 0. Oh, where are we padding extra 0? Originally Hn is 1, 2, 3. These 3 samples over here. And we are padding 1 extra 0 before we are repeating the sequence. Oh, that's it. We're padding the 0 at the end of the sequence. And then we are repeating. So now that we are doing this, and we are using capital N equals to 4, then this Hn minus 1 is n minus 1 modulo 4. And when we are delaying the sequence by 1 sample, because we padded 0, this 0 is being shifted in. And isn't this exactly the original Hn minus 1? And it is. So this gives us a hint why this works. By padding zeros at the back, when we are delaying to the right, the zeros are being shifted, and it will make this n sample here looks like the normal linear shift. Okay, that's the idea. And let's do it again by brute force. So this is circular convolution here again, and that little 4 here shows us that we are assuming our sequences are periodic with 4 samples. The first one, x0 Hn minus 0, this is the same. So the only difference, of course, now is that the sequence that I'm showing you is n equals to 4 sample, not 3 anymore. Okay, so this is 4 sample, there's a 0 here. x1 and h of n minus 1 modulo 4 is also 4 sample, and this looks like h of n minus 1. And now when we add them up, it's exactly correct. Voila! So we know that by 0 padding, we can actually change circular convolution into linear convolution. So then, of course, if you ask me, should we use n equals to 5 instead or n equals to 6? Let us try. So we pad the original sequence with 2 zeros. See? So this is 1, 2, 3 at index 0, 1, 2 with 2 zeros. And now it is repeating every 5 samples. Okay? So what do we do now? Well, let's again deal with this equation. And when we deal with this equation, well, we only are really interested in what happened for the delayed version of Hn. So this is Hn minus 0 modulo 5, Hn minus 1 modulo 5. So again, when we have keep capital N equals to 5, the output of this is 5 samples. This is 5 samples, right? While this previous guy is 4 samples. So again, we have 1, 2, 3 followed by 2 zeros for this first term. x1, which is 1, times Hn minus 1 modulo 5 is 0, 1, 2, 3 followed by 0. Because why? Well, when we delayed this by 1 sample, so 1 samples come in, 1, 2, 3, and then at the back there's still 1 sample, right? Where did this 1 sample came from? It was because we padded 2 samples, but now we shifted 1 out. So there's this 1 sample at index 3 is now here. Okay. So anyway, we have these 2 sequences, and again we add them up, right? We add them up and we get this 1, 3, 5, 3, which is the correct sequence. I mean, the extra 0 doesn't change anything, and we are happy again. So in conclusion is we can 0 pad such that the shifting, the circular shift behaves like a linear shift. That's the general idea. Now, this figure summarizes what we are going to do, okay, in reality. So in most questions is we are given xn that is L sample long. Hn is M sample long. They can be different, right? And we want to produce a sequence that is L, which is the value here, the length of this n, x, and M, the length of this h, L plus 1 minus 1 sample long. Okay? So that's the general idea. And what we should do is that we should pad zeros such that they both now become the same length. Okay? And what is their length? It is L plus M minus 1. So it's M plus L minus 1. So the length is now L plus M minus 1. So I repeat, the original sequence of X is L. We pad it up such that it has this L plus 1, M minus 1 length. The original length of H is M. We pad it such that it becomes L plus M minus 1. Then we take this n point DFT. N is equal to L plus M minus 1. That's the general idea. Why? Because you are going to do element by element multiply. X of 1 multiplied by H of 1. X of 2 multiplied by H of 2. So YK is element-wise multiplication of X and H. And then of course we use n point DFT. Okay, so remember, capital N is L plus M minus 1. Alright, so this is how we use DFT to overcome. And in fact, yeah, this is exactly what we have done for this guy, right? So the original length of the input is 2. 2 plus 4 is 6. 2 plus 3 is 5. 5 minus 1 is 4. So that's why n equals to 4 is sufficient. When we use longer, well, it's not necessary because we are getting zeros at the end of y. So with that, we have shown you how to overcome circular convolution in the frequency domain by zero padding. With that, you can go to look at many of the available resources online to help you understand circular convolution. Thank you.